Chemical Bonds, Chapter 20. This is the second part, Ionic Bonds. Before we start on ionic bonds, let's go ahead and review a little bit. I'd like you to take a moment and write down everything you remember about covalent bonds. Go ahead and pause to give yourself time. Now, I'd like you to write down everything you remember about Lewis dot diagrams. These were both covered in our second session. I also want you to recall that the number of electrons will determine if an atom will bond, specifically the number of electrons in the outermost electron shell. Remember, that can also be called an orbital, energy shells, goes by many names, but the number of electrons in the outermost electron shell is called the valence electrons. The first level can hold 2 electrons, second level hold 8 electrons, third level hold 8 electrons, and the fourth level holds 2 electrons. So you determine the number of electrons, you assume it's a neutral atom, so it'll be the same as the protons, and then you work from the inside out. 2, 8, 8, 2. After that, you use a different scheme. As part of the review, I'd also like you to think about what is the difference between a molecule and a compound. If you cannot recall any of these, please stop here and go back and review, because I'm assuming that I can use these terms and you'll understand what they mean. Chemical compound is 2 or more different elements joined together chemically. It's not saying how chemically, it's just saying that it's being joined together chemically. Covalent bonds, ionic bonds, or metallic bonds. There are other types of bonds, but these are the major ones. Again, a molecule is when the 2 or more atoms covalently bond together, so it's not as generic as compounds. A molecule is a type of compound, but compounds are not molecules. So today we're talking about ionic bonds. This picture is showing tourists visiting the salt flats of Bolivia. Why the salt flats? What's that got to do with ionic bonds? Well, that's because salt is an ionic bond. Ionic bond is when an electron is given away. It's the transfer of electrons from one atom to another atom. It generally occurs between metal and nonmetal. Remember, metal is to the left on the periodic table, and nonmetals are on the right. The compound retains its neutral charge after the ionic bonding, even though you have one that's a negative because it received an electron, and then you have another atom that's positively charged because it gave away an electron. Together, they form a neutral charge. You can often tell ionic compounds because they are often crystalline solids with high melting points. Ionic bonds, again, it's the transfer of electrons from one atom to another. So here we have sodium and chlorine. Sodium has 1 valence electron. Chlorine has 7 valence electrons. As part of the transfer, the sodium loses an electron. So that electron goes over to here. And then chlorine gains an electron. What's that leave behind? This one is no longer here. This one has a full outer shell. See, sodium has 8 in that outer shell, so it's now happy. Chlorine now has 8 in its outer shell, so chlorine is happy. It's formed an ionic bond of sodium chloride, which is called salt. While Lewis structures are more often used for covalent bonds, we can use them with modifications for ionic bonds. Here are some examples. If you were going to do it as a Lewis dot diagram, show the sodium chloride with the plus, and over here you show the chlorine atom with a minus. It has an extra electron, therefore it has more negative charges than it has the protons, in positively charged protons in the nucleus. Therefore, the overall effect, you have 8 negative and you have 7 positive, and so it leaves a total charge of 1 minus. Now I'd like you to draw all sodium chloride. You just saw it there. You can pause and go back if you need to, or you can try again. There's the Lewis dot diagram for a sodium atom and the Lewis dot diagram for a chlorine atom. Put them together and you're left with a sodium ion, now that it lost its electron, and you have a chlorine ion, now that it gained an electron. Let's try another one. Let's try magnesium combined with oxygen. I'd like you to pause now and think about it and actually draw it out, please. Did you get this? Let's try another one. Here's magnesium with 2 chlorine atoms. You can tell it's 2 because the way that works is you have the chlorine, and that 2 means that you have 2 chlorines. So if the 2 comes after, it means you have chlorine and chlorine. So go ahead and pause and create one of those. You get this? You have the chlorine, magnesium, and chlorine. Magnesium gave up 2 electrons, so that's why it's positively charged. It has 2 protons that don't have matching electrons, whereas the chlorine now has an extra electron with no matching proton. So let's talk about the mixture versus a chemical compound. Now that we've talked about ionic compounds. A mixture is when 2 or more combined substances, but each substance retains its own chemical identity. In other words, they did not bind. There's no bonding that occurred, nor ionic nor covalent. So for instance, flour and water. You could separate the two because they did not chemically combine. Why is bond type important? Well, there's significant differences between the physical properties of an ionic compound and a covalent compound. Just like we could predict the family's behavior by knowing the behavior of one of the elements in that family, we can predict what's going to happen in the solution if we know it's ionic versus if it's a covalent compound. For example, let's work out sodium chloride and chlorine gas. Which is ionic? Which is covalent? And how do you know? Let's look at it. So here we have the phase at room temperature. One's a solid and one's a gas. Remember when we said ionic compounds tend to be crystalline solids? Well, which one do you think is the ionic compound? Well, let's also talk about density. One's denser. The freezing point of sodium is very high, whereas chlorine freezing point's very low, boiling point's very high. And whether or not they conduct electricity. One does, one doesn't. Here's what they look like in the solid. You can see where chlorine is tightly packed with the sodium. It's a regular pattern repeating, and this goes on. It's not a certain length. Even though they show it here, it's going to go on even more forever and ever until it breaks off. Whereas the gas, well, here's a separate gas and lots of space in between, which is just a vacuum. For additional information, I urge you to try this spot. It has an excellent interactive flash description of ionic compounds. I hope you enjoyed this little mini lesson on ionic compounds.